Okay, so welcome everyone. Today we will have Babak Ebrahimi introducing Infrastructure Performance Viewer. I will record this session, and in the recording it will not show exactly who is participating unless you are asking question at the end of the performance. Then I give the word to you, Babak.
Hello everyone, thank you for joining. The work of our research is related to sustainability of road infrastructure in Norway, and we quantify performance of material, product, services, systems, and this is done due to the fact that there is a strong causality between sustainability and performance of materials. But later on, quite very soon, I will get to the point that what do I mean by sustainability and performance of materials. And for today's presentation, we're going to have a straightforward and minimalistic agenda, which means that I will go through the background of the research, talking about some of the research topics that we have done and the summary of the results, and at some point in between these slides I will talk about the outlook and the future of the research that we have, and a brief explanation about this research that we have been doing. Our research is dedicated to Norway because Norwegian Public Road Administration is our funder, and this is the nation that we've been dealing with. It's a country with a population of 5.2 million people, which if we put it into perspective, we can say that Norway is the second lowest population, has the lowest population density in Europe after Iceland. And as you can see, the majority of population is located around the coastal area in Norway. And this is a nation that transport or road transport plays a fundamental role in people's life. Around 88% of all motorized travel undertaken in Norway is by road, and about 50% of all goods are transported on roads. And based on the plan that has been explained by the Ministry of Transport and Communication, the idea is to invest more on the Norwegian transport system to increase connectivity and help the nation to get closer together. And by this idea, having this trajectory, the idea is to spend more than 1,000 billion Norwegian kroner over the course of 12 years to modernize infrastructure while developing the transport by providing more effective, more efficient, and greener solutions at the end of these time plan. And if I go a bit more specific, the Norwegian, based on the mandate that the Norwegian Public Road Administration has received by the government, the NPRA, or the Norwegian Public Road Administration, has an idea to enforce various climate mitigation measures. And the idea is to decouple negative environmental impacts and resource use from economic prosperity and social welfare of the nation. And in doing so, the NPRA is tackling various aspects of road infrastructure. Some of these adaptation measures are happening in the in-use phase of road infrastructure that happens by vehicles. And in achieving the goal, the Norwegian Public Road Administration is planning to, in a series of time frames, the NPRA plans to increase the share of biofuels and reducing the non-renewable or conventional fuel sources and at the same time change the powertrains of vehicles by using more hybrid or electrification of vehicles. And at the same time, they have a broader perspective, meaning that they focusing on the entire life cycle of road infrastructure, meaning that they are aiming to reduce the greenhouse gas emission by 40% from the construction of the road infrastructure and by 50% from the maintenance and operation of road infrastructure. However, in this research that we are involved in, we only focus on the the solid infrastructure, road infrastructure, and we exclude this use phase of, or this vehicle part of machineries from the vehicle aspect from our research topic. And to be more specific about our goal of research, the goal of our research is to support the Norwegian Public Road Administration to economically and environmentally plan and maintain their open road network. And the scope of our research is to implement or use two well-established and widely used methodologies that are known as life cycle assessment, LCA, and life cycle cost analysis, LCCA. And using these two methodologies, we're gonna along this utilization, we are planning to compile and assess various data and visualize our assessments. And in this journey, I'm not alone. I am working in a team of 6. I get supervisions from my supervisors, Holger Wallbaum and Rolf André Bohne, from here Chalmers and NTNU. And along this journey, I have 3 companions. They are all PhD students, 2 in NTNU and 1 in Agder, and we are all financed by the Norwegian Public Road Administration. And the idea is to support each other and try not to step on each other's toes, but try to move and help each other out and try to solve a solution from different angles and perspectives. And this collaboration wasn't only on words, however, it was also on papers. So this resulted on various publications and co-publications. And in this presentation, I'm going through 3 of these publications. And you can, if you want, you can also have access to them whenever you would like to. And at the beginning, so now I'll go through one of these papers, which we carried out at the beginning of my PhD life. And at the beginning, we wanted to know what life cycle, or what is life cycle assessment from the Norwegian Public Road Administration, and what is their perspective about this LCA per se. So, and we wanted to know also what software tools are existing, how they've been used, and to what extent they've been used, and what are the gaps, and how we can, at the end, improve these gaps in the softwares. So, based on a discussion that we had with different people in NPRA and Veideråd and the Road Directory, we were able to use 3 softwares: ECHA, which was a Swedish tool, Effect, which was a Norwegian tool, and LISER, which was a collaboration of 4 nations. And in the early assessment of the tool, we found that they are not they've been developed for different purposes. 2 of them were more in the early planning phase, and one was more towards the maintenance aspect of road infrastructure. And some of them were pure lifecycle or pure LCA-based software, and one, which was ECHO, was more economic or social or cost benefit analysis software that at the end got an update and was able to also do life cycle assessment. However, we also wanted to put it in the instead of having the qualitative assessment, we wanted to also do a quantitative evaluation of the softwares. So in doing so, we designed a hypothetical case. So we used one of these road design, this geometric design that is or it is in a manual in Norway, and we use the road class H9, which is a 4-lane road, 2 in each direction, with the travel width of 3.5 meters and hard shoulder of 3 meters, and in total the road width is about 23 meters. And more than that, we use manual N200 to design a pavement, and this resulted in, with respect to the these assumption that we made, that we have this certain ADT class with a certain traffic growth, and so on and so forth, we were able to design a particular pavement based on the manual. However, the software tools were not really the same. So we needed, in order to do the assessment properly, we needed to cut it short or have a really clear system boundary in our assessment. So we use the European standard called 5978, or it's about sustainability of construction works, to define what stages we need to cover. And by comparing this software, we found that only the maintenance aspect of the road infrastructure can be compared. And this resulted to exclude the construction phase, or when you build a new road. And instead of building a new road, we only thought to compare the maintenance activities that happen after constructing a road for over the course of 20 years. And we also considered what is the emissions, or what are the embodied energy and greenhouse gas emissions from the use of hot mix asphalt. So we did this study, and no surprise, we got different results. And we found that asphalt density and asphalt mixing plan was playing a quite fundamental role in this study. And if you think about it, there were only 3 main components in this assessment. There were aggregates from production and use, and if they have moisture, how much added energy we needed to take this humidity from the aggregates. And we had the bituminous binder, we had transportation and energy, which was used in the asphalt mixing plan. And we found that this asphalt density and asphalt mixing plan were the dominant in some of these software, in the 2 of these softwares, that they showed quite different results when we compared the assessment. And more than that, we found that some of these 2 of these softwares were using different embodied energy for bituminous binder. As a matter of fact, they were thinking bitumen or bituminous binder as feedstock energy, which is sometimes there's some discussion among these researchers that we should not consider the bituminous binder as feedstock, and instead we should take it out of this, because at the end we cannot burn bituminous binder. Then that's usually the argument between different papers. After we finally got the results, we were we had a good idea that what we should do. So we started to compile different LCA data, or better say, data compilation in the inventory of our life cycle assessment. So what we did, based on the existing data that we could get from NCC in Sweden and discussion that we had with IVL, we got some information from aggregate production based on different sieve sizes. and also we were able to create different three processes related to bituminous binders. With respect, I mean, bituminous binder in the sense that we have paving grade binder, polymer modified binder, and bitumen emulsions. So we were able to produce asphalt, and also we create some process related to the asphalt mixing plant. By having all these ingredients for producing or creating road materials, we also created processes related to construction machineries. Meaning that we created inventory related to different non-road mobile machineries like articulated wheel loaders, articulated trucks, soil compactors, pavers, graders, and so on and so forth, that we could somehow getting closer to building the hypothetical or existing road infrastructure. However, when we got to the point that we could design a pavement or doing all the earthworks assumption that we need to do, we came to the point that we had a very vague understanding about the maintenance or lifetime of road infrastructure. We know that since road infrastructure is built, they go through a almost never-ending spiral cycle of maintenance activities. However, we were really curious to know how we should handle it, because from a scientific point of view, we needed to be quite precise or have a quite reasonable idea about these maintenance activities along the road. And based on the study that we've done and this research that we carried on, we found that maintenance activities or asphalt work corresponds to 25% of total maintenance costs in Norway, which is playing a fundamental role if you think about road infrastructure as a somehow having a long-lasting service life. So they have a never-ending maintenance there are never-ending maintenance activities along their service lives. And more than that, the traffic volume has been constantly growing since we had only the access to some certain year period, but the traffic volume has been constantly growing in Norway. And interestingly, in the central, western, and southern regions in Norway, the traffic volume, the growth of traffic volume was even higher than the national level. And if we think of this at the end of the year, we need to know how fast or slow some certain roads in some certain regions or districts are going to, or sections going to be maintained, and what is the intervention level that we need to take. And going back to the same graph, if you look at this national level growth, you can see that if you divide it based on the vehicle weight of vehicles, you can see that the heavyweight vehicles, the growth of share of heavyweight vehicles is twice as many as normal or lightweight vehicles. And then more than that, there is a certain increase in service life or requirement from road infrastructure. Some roads need to be improved due to increase in the traffic volume, and we need to increase the bearing capacity of a road, or we need to widen of the road, and somehow different changes happening inside the road network that subsequently has a knock-on effect on the neighboring networks. And more than that, the effect of maintenance activities on road user. Whenever we close the road, this road has an impact on the user, so they need to take a detour, or the travel time is increasing, the wear and tear of vehicle is increasing, and at the same time results in increase in emissions and fuel consumption of the vehicles. And also, when we got even more deep down in the research, we found that there are some ideas about what will be the nominal lifetime of materials, specifically what is the nominal lifetime of asphalt surfacing. but we did not know what will be the technical lifetime of asphalt surfacing types. This resulted in having a series of discussions with different people in NPRA, Veidirektoratet, and some consultancies to see what can be done in order to find the best approach, visible or feasible approach. So based on literature review and a discussion by payment management system people in NPRA, we found that we can technically achieve such a lifetime estimation, at least going to estimate what will be the lifetime of asphalt surfacing, or technical lifetime of asphalt surfacing types in Norway. And in doing so, we needed to have a climatic zones data, signed speed limits, asphalt surfacing type, annual average daily traffic, traveled way width, and road condition measures. These things were already existing, or in the data catalog in Norwegian Road Data Bank were existing, but some of them did not. For instance, climatic zones didn't exist, so we needed to find another approach to solve the challenge. And more than that, road condition measure was quite controversial for our study, because we needed to see what will be the technical lifetime, in a sense that when pavement distress occurs. And as you may know, there are gazillion number of distresses, and one can be due to pothole, cracking, spring cycle, and then bleeding, so on and so forth. However, in this study, we narrowed it down and decided to only focus on unevenness, transverse unevenness, which is also known as rutting or wheel path deformation of pavement, in order to use it as a response variable to say if when a particular paved or asphalt surfacing reaches or passes a certain threshold that is already explained by with the maintenance manual in Norwegian Public Road Administration. So we started our journey. Our end goal was clear. We wanted to know what is the technical lifetimes. But we get to that point, we needed to start collecting the data. And in doing so, we use Norwegian Road Database, which is also known as Norwegian Road Database, NVDB. And however, this data that we collected did not communicate it. They didn't at least have a foreign ID that they could be able to be used, like in some softwares like SQL server or these other data transformation data. So in order to make the data transform the data in order to communicate with each other in a really rational or logical way, we use geographical information systems, and we use ArcGIS and FME, these two softwares. And at the end, after several or sequential transformations, we were able to create an attribute table consisting of various indicators, like what is the pavement type, what is the aggregate maximum aggregate sieve size, what is the binder type, like what is the asphalt speed limit, and so on and so forth. And then we had this attribute table that we aiming for all the way at the beginning. And after having it, we perform one statistical method, which is known as survival analysis. And in that method, we use Cox proportional hazard model and use our program language to quantify these technical lifetimes. And we didn't aim big, so we decided to go for only 3 counties in Norway. And we also, as long as we were using rutting as a response variable, so we decided to think of road infrastructure or asphalt surfacing that they were used for AADT above 3,000 vehicles. And by having these sort of limitations, we ended up with these, you can see these paved lines, these red lines on a map. So these were the roads that they've been exposed to traffic above 3,000, ADT of above 3,000 vehicles. And as I mentioned earlier, we did not have climatic zones in our data. And so in that, due to such limitation, we decided to go for these three counties due to the fact that they have certain climatic differences. They had about 2 degrees temperature difference and to some limiters of precipitation differences. And we use this data from Norwegian Meteorologic Institute to support our analogy. And after that, we ran the program, ran the data, and we were able to create some certain results. And the beauty of this method is that you know what is your independent or dependent variable, which is about the service life or technical lifetime of a product payment, but at the end you can also explain it by some certain explanatory variables, like what is the, for instance, I want to know what is the service life of a asphalt surfacing in a particular location with certain sign speed limit, aggregate upper sieve size, and administrative bearing capacity class. So here I only show one example. We consider an asphalt surfacing which was using such AADT between 10,000 to 20,000, located in Sør-Trøndelag. Signed speed limit was 50 km per hour, aggregate upper sieve size was 11 millimeter, and administrative bearing capacity class was T1050. And by by fitting the data to such requirement, we ended up with for 3 different asphalt surfacing types, the median lifetimes became almost 5 years old, 5 years. And you might say, okay, why asphalt concrete is having the same service life? I mean, asphalt concrete by paving grade binder has exactly the same service life as a stone-mastic asphalt with polymer modified binder. Well, this method that we used was based on a stochastical analysis. So we did not have a deterministic approach to say that asphalt or stone-mastic asphalt should have follows a certain distribution. And we let the software, let this method finds the distribution or likelihood of failure of a pavement based on the existing data that we have. And based on some supportive data, we could find why such differences can occur between different types of pavements. For instance, if you look at this AADT, the range is about, one certain asphalt asphalt surfacing can be in the 10,000 and the other can be in 20,000. So the difference is really wide. Or in other way, this classification that we use or is introduced in Norway is really wide. So we weren't able to cut it short or have it really in a smaller intervals. And more than that, the traveled width was playing a quite controversial role in the data that we had. Meaning that if we had narrower road, the repetitive or fatigue loading due to repetitive loading of the wheel on some certain wheel path was increasing, which was resulting to change the profile of this rutting that we have, and also duration of the winter, or speed and some other parameters were affecting this longevity of the asphalt that we have. And there were various findings were resulted from the study that we had, and just I bullet point 5 of them here. Based on this, the results that we got, we found that there is an inverse relationship between asphalt surfacing lifetimes and traffic volume, meaning that having the Shortest lifetime of asphalt surfacing means that you have higher traffic volume and vice versa. If you have a shorter or if you have longer traffic asphalt surfacing lifetimes, means that you have lower traffic volume. And also maximum aggregate seam size plays a fundamental role. If we have a coarser aggregate, we could expect that the longevity of the asphalt surfacing was longer due to the reduction in abrasion of asphalt surface. That really decreased this speed of rotting. And more than that, we found that the asphalt surfacing that are in the colder climate, like in Troms, have a shorter lifetimes, and this was because of longer duration of winter, longer duration of using studded tires per se, and also travel weight width could influence the longevity of surfacing, and also based on the result that we could find, we could determine the frequency of asphalt surfacing, meaning that we could use such data and use it in some to identify the section, because we were using GIS data, and by this GIS data we could identify those sections that they have the highest probability of increasing asphalt surfacing, and the results can be used for this pavement management system to somehow show that what will be the probability of having the shorter lifetime or longer lifetime for some certain suggestion that this PMS 2010 software provides. So we can somehow use it in such manner. And also the results from this study can also be used to estimate this optimization assessment, to focus on how frequent we need to do the maintenance activities and what would be the best asphalt surfacing for that particular period of time with the particular condition to reach our to have the lowest cost and lowest impact. And at the moment we are downloading more data from the database that the Norwegian Public Road Administration provided, and now the idea is to go beyond these 3 counties and beyond only rotting as a surface, as a response variable. Meaning that we are aiming to quantify this asphalt surfacing lifetimes on the entire nations, and with more, and in considering rotting, longitudinal roughness and unevenness, transverse unevenness, and microtexture of the surfacing, to see how would be the technical lifetime of asphalt surfacing in different areas in Norway. And also this summer we got a really good access to some certain data or data from NTNU, which we ended up using it and sending it to a conference peer-reviewed in TRA, in a way, Transport Research Arena. And in the idea that we had for this data that we collected was to introducing a screening emission accounting of different construction machinery, meaning that we use this Norwegian construction, because we use the Norwegian construction machinery data, and we wanted to have an alternative approach than prior studies, meaning that we wanted to have a top-down approach instead of bottom-up, because in most of these prior studies using this method called PEMS, portable emission measurement systems, that they put it in the vehicle machineries, and they measure the on time based on some intervals, that measuring what are the pollutants that are going out from the tailpipe of vehicles. However, this assessment requires very long or many observations, different types of machineries, because the machine which is used is only operated in one certain condition. Different drivers, different soil or climate, tire pressure, and the idle time, transient time of engine affect this emission of a particular machinery. So therefore, we decided to use the data that we could get from the Norwegian, Norway, from construction machinery. And the beauty of the data that we got was that they were using effective hours instead of a normal hour. And this effective hour was the represented time a machine is operated efficiently, including both direct production time and other operational time. And this direct operation time was the net operation time, which means that the machine is used effectively. But the other, or this other operational time was referring to the additional operation time, like some activities that you may do during the work. Here, the data that we got were from 3 or 4 articulated third-wheel loaders. And for the case of wheel loader, we can say that the net operation time is when the wheel loader is driven to piles, filling up the bucket and drive to dump truck and empty the bucket. But if you consider this additional, what will be the additional time during this operation phase? I mean, we can say that the time which is spent by wheel loader to trim the piles or weighted the whole truck. So, or the waiting time that this whole truck comes in. So then the duration that the machine goes to the idle phase. And then we use this data, and then we have also we use a certain machinery. The machinery that we use were in the assessment variation of the load. We knew that the variation of load substantially affect the fuel consumptions, and based on this construction machinery, we knew that they operating in some particular condition. Here, these 4 articulated wheel loaders were operated in a quarry to move a stone material. So they had a really certain condition. And more than that, we knew that what is the density of this. We had the particular or somehow vague or quite good assumption about what will be the density of some materials. And then we use this data, and more than that, we use the emission factors that were documented in this air pollution emissions or air pollution emission standard or guidebook that is published by MEPEEA, which stands for European Monitoring and Evaluation Program and European Environmental Agencies. And by fitting all this data to some certain equations, simple equations, we created this fuel, what will be the fuel-based emissions per economic lifetime of machineries. And no surprise, when a vehicle, when a machine consumes more fuel, means that it emits more pollutant. No surprise for that one. But this emission, the share of increase in amount of pollutant was sometimes depending on the deterioration factor that the machine could go through. This means that for some certain pollutants, due to the deterioration of engines, more pollutant would result as in the tailpipe of engines. And more than that, we didn't stop there. We continue, and we also use the results to show that what the effect of load capacity and gases emissions. Because in the previous one, we showed that what will be the emissions per effective hour. However, we decided to go further and say what will be the emission per moved volume or load capacity of different trucks, different wheel loaders. And as you can see, the results show that although bigger engine size and higher fuel consumption results in having higher total in-use emissions, the total capacity of equipment can, differ from one machine to another. And this means that as the efficiency of machine in the unit of liter of fuel per cubic meter of moved volume got higher, the corresponding emission showed lower values. Yeah, and you can see the results, how it shows, because in the previous picture, emission per effective hour of machine A was lower than the others, or had the lowest emission compared to the other. However, when you compare it based on load capacity, you can see that machine B and C outperform machine A and D due to different load capacity that they have. And based on this method that we use, we're gonna continue, and now we're gonna follow our dream and publish a paper soon, very soon, based on life cycle assessment of construction machinery, meaning that we, instead of only dealing with let's say this area, which was the main focus of our study, in which we meant that what will be the direct emission from the operation of machineries. Now we aiming to consider the whole life cycle of construction machinery, also known as non-road mobile machinery, to say what will be the emission in different stages or different life stage of machinery. What will be during the use phase, how often we need to do the maintenance, repair, change services, and what will be the effect of use phase compared to the other life stages. And by that, I think I can conclude here and say thank you. And now I'm open for all your questions, if you have any. Let's see.
We can do the questions both in writing and in oral, if anyone wants to join in orally.
I have some questions.
Yes.
My name is Tom Nurbeck, and I have just taken on the role as a project leader for the sustainable infrastructure part of the E39 project. Regarding the asphalt, it is known that it's heavy vehicles that tear down the asphalt a lot.
Yeah.
You know, you said that you had 12% of heavy vehicles on all of the roads. Is that so?
No, I mean, let me go to that one. I need to. Are you referring to this one or?
Yes.
Oh, what's that one? Okay. No, this one.
What I'm interested in is that, you know, for instance, like Finland, they have a limit of 70 tons. And this is very hard on the asphalt. In Norway, we have 50. And then I'm thinking, you know, if we go to a future with more autonomous vehicles, smaller vehicles, say 25, 30 tons, would that increase the lifetime of the asphalt substantially?
I don't want to say for sure, but I don't think so, because if we increase the heavy loading, because heavy loading is the main reason of the deterioration that we have in asphalt surfacing, especially if we have the subsoil subgrade. But in the study that we carried on, let's say here, the method that we used was based on a stratification method. So we stratified the data based on traffic volume or total annual average daily traffic. But we, as an explanatory variable, we considered effect of heavy weighted vehicles. So we used effect of heavy loading in our study with proportion to the total average daily traffic to explain if we have a road which is having a shorter period of lifetime, or let's say, let me go to this one, which might be a bit better. Yeah, like this mastic asphalt. You can see it was 4.2, but this asphalt surfacing, asphalt concrete has 4.2. I mean, they had exactly the same surface life or technical lifetime. And the reason why that I also forgot to mention was that these asphalt concrete was close to these 10,000 AADT total annual average daily traffic, but stone mastic was close to 20,000 AADT, and also it has highest share of heavyweight vehicles compared to asphalt concrete and stone mastic asphalt in this with the paving grade binder. But that, yeah, for sure, increasing heavy traffic volume heavyweight vehicles substantially affect this repetitive loading, and and in combination with different types of fatigues and so on and so forth, maintenance backlogs, we might end up with a really poor surface, more frequent and shorter lifetime of materials.
Okay, thank you. And then I have one more question. Yes. If you could go to the life cycle analysis of the machinery, that slide.
Yes. Is it this one or next one? Next. Yeah. Oh yeah, this one. Yeah.
Yeah, that one. This one. Yeah. Here you are looking at machinery powered by fossil fuels.
Yes.
Yeah, but there are initiatives, promising initiatives regarding zero emission machinery.
Yeah.
That would be very interesting.
Yeah.
To have an analysis of that as well.
Exactly. I mean, I was talking to MF, what was it? MEF, I think it's called, the machine for
machine entrepreneur.
Yeah, exactly. Yeah, I think it's called the Norwegian Association of Heavy Equipped machinery, or something.
Yeah.
And
I know.
They had such an idea to using battery-based machineries, or some of them were thinking of using plugged-in, based on discussion that I had with them. But they are not still existing. So in order to find this actual solution, or this LCA that we are doing, is the idea is to provide the baseline emission, or in a way, for Norway, because we are using Norwegian data for operation phase of construction machinery, and we can somehow say that if you further on consider electric with the electric power drain equipment, how much gain you will end up with. So that's for sure. It's very helpful to know.
And just one more thing. Yeah. If you say that we succeed in getting this down to zero emission, how much would that mean for an average 1 kilometer of road? How much of the total would that reduce, approximately, just a ballpark figure or something?
Is it? But do we think about the building or construction phase, or the building a new road, or is it during the maintenance activities? Because
well, let's say the building phase.
I mean, building phase usually, based on literature. I need it. This is. I mean, let's start with the literature study. Based on literature study, it says that earthwork activities, or earthworks, has the highest contribution during the construction phase. And if we consider it, but also it very depends on the topology of a land, the amount of cut and fill we might have, and also the severe or harsh condition of the area. And for sure, I think if we can lower down this, or at least make it, carbon free, we can technically reduce the greenhouse gas emissions, substantially in this regard.
Yeah, then you're talking double-digit figures. Yeah, good. Then it's substantial. Good.
Yeah.
Thank you.
Yeah. Yeah. Let me go. I think I received some others. Yes, I got the. Oh yeah.
Do you see my questions?
Yes, there's a question. It's asking about effect is being updated. Do you have an input that I should make available for our colleagues? I don't know if it's gonna be nice if I can get the access to that one, because there was one limitation with the effect that we had, was that it was really aggregated. It didn't provide the really, I want to see why we have maintenance interval of 5 years, why I cannot play around with the data and say that I'm using a certain type of mix and I'm sure that it's not going to be 5 years, it might be 6 years. But I can understand effect. The idea of using effect was to be used for, early planning stage. And in the early planning, you should be very careful and try not to make a really wrong estimation. But it might be really beneficial to, have effect, but in other stages like maintenance activities or some other phases that you can somehow, because that's still the same platform and many users know it and it can help quite a lot. And I think it's the same, the machines. Oh, maybe I should read it. The machines that had the best results. Do you have any suggestion on how we can take description into our maintenance contracts? Well, unfortunately, the data that we got were primarily related to, let's say, this only earthwork phase, and we did not have much information in the maintenance maintenance activities like these pavers, rollers. However, based on the data that we could get from IVL, we generated these data, but these are based on median performance and they are not really adaptable with I don't think it's gonna be a really wise decision to use it for the Norwegian case, but it is for sure can be used and then later on updated. Oh yes, yeah, that's sure. MEF, yeah, forgot that name. And 2 or more people are typing. I don't know. Let's wait.
If anyone wants to ask a question also, you can do that.
Yes, for sure. The data, the question is there potential to apply your research to surfacing on bridges as well as roads? Yes. This method that we use were technically only focusing on open road infrastructure. So we excluded tunnels and bridges from our dimension. And we decided to say, okay, what is there? Because the bearing capacity and so many things are influencing quite a lot the service life of, and also the design condition is quite different. For instance, for bridge, you need to have certain particular surface texture and so on and so forth. And also for tunnels, you need to have fulfill some certain requirements. However, it is really easily adaptable. We need to just modify the beginning part. Instead of focusing on the tunnel, only focusing on the open road infrastructure, we can shift and do it for bridges. Yes, for sure. And we can also use this information that we got from what is it called? Rotting, roughness, and texture to back up our our analogy for the study that we are performing. And yes, yeah, and Holger highlights that the current findings on machinery just make clear that we need to put more emphasis on the topic. It would be interesting to drive this further. Example, the collaboration with Statens vegvesen in a master thesis, etc., etc. So this is quite a very, yeah, we are going in that direction exactly, because if we want to reach the mitigation goal that the NPRA is aiming for, especially during the construction phase, by 40% reduction, we can technically, yeah, construction machinery takes a big chunk of this, has the biggest size of this cake of contribution in the greenhouse gas emissions. So we can somehow, yeah, we should lower it down. To some extent, it's going to be beneficial for us. Yeah, maybe I should. Yeah, I'll take that too. Yeah, should I read it? Yeah, thank you. And then, yeah, then we have also next presentation in January 26th at 3 Peter Nilsson. The topic is laser weld sandwich steel elements. So please feel free to join us. And thank you, Gaylord. And then also Rolf André Bohne says we have just started a small project on CO2-free construction, internally founded, and we'll be happy to collaborate on this. I've just hired to research assistant. Yeah, so the topic is going. So we need to be happy about this. Yeah, sustainability aspect from the environmental perspective, and yeah. And yes, thank you very much. Thank you.
Okay. I think then it's time to start concluding this presentation. Thank you for a very interesting presentation, and I think as you see of the comments, we will follow up on several of the topics that you have presented today.
Thank you.
Yes, and as I also wrote in the commentary field, the next presentation will be in 1 week at 1 o'clock when Peter Nilsson will present laser welded sandwich steel elements. So I hope most of you will be back then. And by that I say thank you for today, and see you again on the next topic. And thank you, Babak.
Thank you very much for having me. Yeah.